Yeah. So they'll either fail on the task or they'll be successful on the task. If they are failing on the task, we give them 0 points. If they are successful on a task, we give them a 1 point. This is the rule that we have. Okay, this is our rule. Okay, I don't need to put a bracket in this. There is no math. So this is the rule that we are applying. We are applying this rule to what? To the sample space. Okay. Now I create a new step. I call it Y. What is Y? Y is number of points earned. Okay. Now in this experiment, if I am doing only 2 tasks, Y will take a value 0. This is possible if they fail on both the tasks, right? Right? That is, Y will take a value 1 if SF or FS, right? Y would take a value 2 if the outcome is SS. All possible outcomes are done. Now, what I can actually do is I can ask for probability associated with Y. Now, probability that Y will take a value 0 is happening only once, that is when they fail. Now, this is one of the 4 outcomes. So, and all the outcomes are equally likely. That's what we are assuming, that success is as likely as failure is on both the tasks, right? So, this is 1 by 4. This is happening, you get 1 point if here as well as here, right? So, this is 2 times out of 4 times you are getting 1 point. 1 times out of 4 times you are getting 2 points, right? You do both the tasks successfully. Now, what am I doing? Probability of, what is Y? Y is number of points earned. Is this number of points earned there in the sample space? No. This happened when I applied some rule to the sample space, right? So now I'm not talking about probability of 2 successes or SF or FS or FF. I'm talking about probability of number of points earned by a person. Okay, so the chance that they will earn 0 points, 1 point or 2 points is what I'm talking about. So this particular variable Y, number of points earned, is a random variable. This variable is giving us and I'm not now talking about probabilities associated with this random variable, right? So because this is a random variable, because I have applied some rule, a real valued function, if it is S is equal to 1, F is equal to 0 is the real valued function that I have, right? And this function, if applied to this sample space, this is the random variable I get. Now I'm talking about probabilities associated with the values of the random variable. Now, can I actually think of random variables? One of the common examples that comes to my mind is, say, and this I have given in the previous classes amply, is suppose I'm taking, I want to know what is the mean emotional intelligence of Mumbai college students. It's a valuable information for me. What do? I take a sample of say 200 or 100 college students, I compute mean, that is the X bar. I call this X bar 1, right? Now, if I take another sample of another 100 college students, will the new X bar be the same value? No. This new X bar would be a different value. If I take a third sample, will the third sample give me the same x bar? No. So my sample's mean changes as I obtain the next sample. So if I keep on changing the sample, the mean of the sample is a different value. If I draw the sample again from the population, the mean value that I am getting for the sample is a different values. So my sample mean is a random variable. If I understand that the sample mean is a random variable, then I can actually ask the same question about sample mean. What is the probability that I will observe a specific value of sample mean? Which is an interesting question, which would help us in making a lot of decisions about the parameters by using statistics. Okay. So, well, this is random variables. Now, random variables. Now, what I actually say is, if y, this is y, and this is probability of y taking a specific value, then y takes a value 0, 1, and 2. This is 0.25, this is 0.5, this is 0.75, this is 1. That's the highest value of probability. So, y taking a value, this is how I can plot the distribution. So, this I call distribution of probabilities associated with y, right? And then what I need to do is I need to write some function fx, such a way that if I enter a value of x in that function, I will get px for that value of x. Okay, and that function is called as distribution function. So if I enter 0, it should give me f of x is equal to 0 is 0.25. Now this f I should be able to write. The formula that gives me, if I enter 0, gives me 0.25, I should be able to write, or f of x is equal to 1 is equal to 0.5. Now I should be able to write this f in such a way that whenever I enter these values, it should give me the probability associated with this value. So this is called as distribution function. This formula is called as distribution function. Now let's look at the probability distribution. What is probability distribution? Probability distribution is basically this kind of idea where if I know the values of random variables, it's a formula that gives me, if I know the values of the random variable, it's a formula that gives me the probabilities associated with those values of the random variable, right? It's a formula that gives me probabilities associated with the values of the random variable. Now, say, for example, if I'm rolling 2 dice, this is the example that we've discussed earlier, so I'll review with that example. If I'm rolling 2 dice, then there are total 36 outcomes, 6 into 6. Okay. Now let's look at the sample space. Right. Sample space consists of, say, the first results in 1 and 1, the second results in 1 and 2, or 2 and 1, then 1 and 2. And say suppose I sum the uppermost surface. These are the uppermost surfaces of this. So if I sum the uppermost surfaces, this results into 2. Right? 1 plus 1, 2. 2 plus 1, 3. 2 plus 1, 3. So then 4. In how many ways I would get 4? 1, 3. 2, 2. 3, 2.
3, 1.
Sorry, 3, 1. Done. So these are the ways I get 4. Then if I want 5, I get it 1, 4, 2, 3, 3, 2, 4, 1. Right? 6. 1, 5, 2, 4, 3, 3, 4, 2, 5, 1, 7, 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1, 8, 2, 6, 3, 5, 2, 6 because 1, 6 won't give us 8. 3, 5, 4, 4, 5, 3, and 6, 2. 4, 5, 5, 4, and 6, 3. 10 is possible by 4, 6, 5, 5, 6, 4. 11 is possible in 5, 6,
That's what she said.
6, 5, and 12 is possible by 6, 6. Right? So this is the sample space. It is 36 outcomes. 1, 2, 3, 4, 5 up to 36. Right? These are the values of random variable. What we are doing is, this is x or random variable. Right? Now I can actually work out the probabilities associated with these values. That is, there are out of 36 events, there's only once I'm getting a value of 2. Right? So this probability is 1 by 36. This is 2 by 36. This is 3 by 36. This is 4 by 36. This is 5 by 36. This is 6, 1, 2, 3, 4, 5, 6 by 36. This is 5 by 36,
6.
4 by 36, 3 by 36, 2 by 36, and 1 by 36. So, getting a total of the uppermost surface of dice equal to 2 has a probability 1 by 36. And so on and so forth. Getting a total of 7 is 6 by 36. Getting a total of 10 is 3 by 36. Now I should be able to write a formula. So this is probability of x taking a value x, right? So I should be able to write the formula f of x, or probability that x takes a value x is what? If I write a formula, then it will give me some answer which is useful to me. So this formula for me has a very simple structure. In all the cases, the denominator is 36. Okay, and so I am doing 6 minus absolute value of x minus 7 would give me probabilities. Okay, now this is, say suppose I enter a value 2, 6 minus 2 minus 7 upon 36 is 2 minus 7, 5, 6 minus 5, 1 by 36, right? If I take if I ask what is the probability that x takes a value 8, then it is 6 minus absolute value of 8 minus 7 upon 36, that is, this is 1. 6 minus 1 is 5 by 36 is what the probability of of getting 8 is, and so on and so forth. So what I can actually do is I can write a formula. This formula is something, this will work if x is equal to 2 to 12. Okay, this will not work in any other condition. Okay, else it is 0. So probability of x is 0 if x is smaller than 2 and greater than 12. Right? Fine. Now this is my formula. This formula is called as distribution function. What is a distribution function? distribution function is that formula in which if I enter a value of x, returns me the probability associated with that value, right? That's what is distribution function. So any distribution function, say binomial distribution function, p raised to x, 1 minus p raised to n minus x, gives me probability associated with x if x follows binomial. Or normal would do the same. The normal distribution function do the same for me. So basically what distribution functions do is if I enter a value of x in the distribution function, they return me the probability associated with that value. Okay, right. So I have already uploaded a YouTube video about how to use this to write a particular R code and write a function and stuff like that, right? The next problem is expected value and variance. Expected value and variance. People who have not attended any of the previous classes, are you understanding? Because I'm doing it for you primarily. Are you following? Please ask questions if you're not following. Okay. Expectation x, expected value. Expected value is an important concept and so is variance. This is read as expectation x. This is read as expectation x. Expectation is the average. Expectation is the average. So generally how do we compute average? Why do we need expectation? How do we compute average? We compute average by doing simple stuff. That summation I is equal to 1 to n xi divided by n, right, is our x bar, right, is our x bar, is what our average is. Now say suppose I have a data like x takes following values 2, 2, 3, 4, 4. Okay? These are the values x is taking. Okay. Now right? 15 is the total. Fine. Now, if I have to do the average of this data, summation x is equal to 15, right? Now, if I have to do the average of this data, what do? I will do sigma x and I'll divide it by n. That is, my n is 5 and this is 3. Okay. Now, instead of that, I can actually write it. It says summation xi. So I would write 2 plus 2 plus 3 plus 4 plus 4 divided by n, that is 5. Now this thing I can actually write separately and express it as 2 has occurred twice, so 2 into 2. 3 has occurred once, so 1 into 3. And 4 has occurred twice, so 2 into 4, to do these additions, divided by 5. Okay, which also means that if I write this together, then I can write it 2 by 5 into 2, right? Plus 1 by 5 into 3, plus 2 by 5 into 4. Now, what is this 2 by 5? 2 by 5 is probability associated with 2. 1 by 5 is probability associated with 3. 2 by 5 is probability associated with 4. So what I am actually doing is I am multiplying x by its own probability, right? So suppose 2 by 5 is,
The probability of 2.
yeah, okay, computed
This will be 0.4. Yes.
0.4.
Yeah.
0.4 into 2
0.8.
plus 1 by 5 is 0.2
0.2.
by 3
0.6. 1.6.
and then
This will be 0.14, 1.2, yeah.
that's what our mean is, right? The whole point is, when I was computing this mean or expectation, I was using probability. So what I was doing, this is my px, and I'm multiplying that px by x, and then I'm adding them, right? So I'm summing x into px. So expectation x is equal to summation of x px. Why x px? The idea is very simple. When we have distribution functions, okay, the distribution function, sometime back we had a distribution function, probability that x takes a value x is equal to 6 minus absolute value of x minus 7 upon 36. This is the px. I want to know the mean of this random variable. Then I actually put px here and compute it, because I don't have n available. It's not a sample, it's a probability distribution. So if I want to know the mean of a probability distribution, I take the expectation of it. We will do this expectation business for Poisson. We have already done that. And so you can understand that if we put probability distribution function in P at the place of Px and solve this, you get the expectation of x, where x is a random variable. X is not a data set, x is not a value of sample. X is a random variable. So for that random variable, if you want to know what is the expectation of that random variable, then you do summation x px. There are two kinds of random variables. So if we are doing, this is useful for discrete. For continuous, if random variables are continuous, then it's integration from negative infinity to positive infinity, x into px with reference to, with respect to x, right? So this is what expectation would be for continuous random variable. Well, we have already discussed the examples of this amply, and so I don't wish to repeat those examples here again. The variance of a random variable is obtained by x is obtained by expectation x minus mu the whole square. That can be written as expectation x square minus expectation x the whole square. Expectation of x square minus expectation of x the whole square. Okay, so we do x squares and take expectation of it and subtract the expectation of x square from it. Expectation of x square is mu. Okay, so basically mu square, right? Expectation of x is mu, right? This is variance. Now, one simple idea that we need to understand is variance is also expectation, and your average is also an expectation. Variance is the expectation of deviation from mu. So squared deviations from expectation of the value of a random variable are variance, whereas routine expectation is just expectation of x. Whereas variance is squared deviations from the expectation. Expectation of a squared deviation of from expectation. Right? So this is what variance is. So variance is also an average. That's why when you compute variance, you actually divide it again by n. Summation x minus x bar bracket square upon n is your variance formula, right? So when you divide anything by n, you get an average. What is the average you are taking off is your numerator, right? I think this is what we have done in the first few classes. Then this conditional probability is something that I have done and it's available on our videos, right? So I need not do conditional probability because after this what we did is Bernoulli random variable, then binomial random variable, then Poisson random variable. Then we also discussed the difference between the discrete distributions and continuous distributions, and then we did lot of continuous distributions also. And then we did conditional probability. What perhaps you not we need to do is conditional expectation and conditional variance. I don't know whether you have done this or not. If you have not done conditional expectation and conditional variance, we will do that. You have done that, right?
Yeah.
Yeah. And then I shall upload them on the YouTube channel. Right. Thank you. Any questions? Please ask.
And so we have solved some also.
Very good.